It's part of revision anyway, so we covered this just today. Thank you very much. Every so often I'll need those kind of prompts, please. At least somebody is paying attention. Right. So if you're driving, you could think of zeros as enormous potholes. So you don't want to drop into that. It will bring your journey to an end very quickly. And poles could think of literally that, like trees, big light poles in the middle of the road. You don't want to get in the way of those either. So the whole thing about knowing where the poles and zeros are to try to avoid the issues, to avoid both of them and navigate your way between where there are neither poles or zeros. And we saw, for instance, if you were to take a transfer function, an arbitrary one that is up there, okay, and that you could factorize both the numerator and the denominator. And remember that there's nothing to prevent factors from being complex. Okay, get used to complex numbers. They are there all the time. And especially in electrical and computer engineering, they mean specific things too as well, depending on what you're doing. You can plot the poles and the zeros into something called the S-plane, right? S because we are dealing with the Laplace transform, and the plane plots the real part and the imaginary part of each pole or zero, each solution to the transfer function. And we said we plot the poles, usually you plot the poles with an X and a circle around it, and the zeros with a dot and a circle around it. Okay, so like in this particular one, this diagram had poles at what do you call it? -1 plus or minus 2j, and then it had a 0 at -4. Right, and then I said this one, you could try this, or you could use MATLAB, as the case may be. If you have to work out this manually, usually if there's an exam question that requires you to solve some sort of equation like this, these sort of things, you try S equal to plus or minus 1, well, of course, 0 plus or minus 1 plus or minus 2, usually. After you do that, so one of those things most likely will work for a typical example. And then if that is a root, then you're down to S cubed. And from there, you could use the usual trial and error methods, and then at square, once you reach S squared and so on, if it can't factor, then the usual formulae to get you around that. Again, it's unlikely, I'm not interested so much in the algebra of you being able to solve a fifth order equation to see if you know how to find roots and the like. But there are certain operations that I want you to be able to do. So for instance, having found the root. So let's say I was to give you a question like this, and you found the roots, but you made a mistake in whatever it was. If you find the roots, make a mistake, but afterwards I want you to, let's say, find the inverse transform or do some sort of manipulation. That's a separate issue. So if you make mistakes in calculating the roots, either the zeros or the poles early on, then the subsequent part of the question asks something like, okay, so what is now, if G of S is this, what is GT? So you have to find the inverse transform, which we're coming to. Then that is a separate issue. I will use whatever answers you had before, if even they were incorrect, and check your technique going forward. All right. So in this particular case, this question, there was a hint that there were two poles at -1 and -2. So you have to, if one pole is at -1 and -2, that means that S plus 1 and S plus 2 are factors. So you use that, you divide the denominator by that, and then you get another polynomial in S squared, and so on, and then you will solve it. You know how to do all of these things. So in this particular case, this problem had two complex zeros, and it had the poles that are not complex, we call these, this and this, we call those simple poles, and of course these are complex, right? Those are complex. And then just for illustrative purposes, you can draw them. The diagram is a little bit small. So X's mark the poles, and we normally circle them. This was generated using MATLAB. MATLAB doesn't circle it, but you can ask it to, and it circles the zeros because a dot on the paper will be near invisible. So you have to circle to at least say where it is. We also circle manually. If you're doing this thing, circle the X's as well. It makes it easy to locate. All right, and always draw, whenever you're drawing the diagram, always draw the origin. As we'll see a little bit later on, where the poles and the zeros are, especially the poles compared to the origin, is very important. The zeros make the thing shut down, which is good to the extent that certain things can't happen, but it's bad because if you have a system, you don't want it to switch off without you knowing. The poles are the ones that tend to run the thing into V, saturation, over voltage, and the like. Those are the ones that you need to be careful of. All right? Right, and of course, remember what we said last, that we go from one domain into another where the solution to the problem is easier. So we take a differential equation, we apply the Laplace transform, and we enter into the S domain or the Laplace domain, and we can manipulate, as we saw with partial fractions and the like, but at some point in time, you have to come back into the time domain. That's where we are. So you do that. If you like mathematics, you do it by doing an inverse integral. Notice for this one, the limits here, it's some complex integrals. Before, when you were going in the forward direction into the S-plane, you had just minus infinity and infinity. Here you have to integrate between two complex limits. And then, of course, the sign here is reversed. Minus e to the minus st gets you into the S-plane. E to the plus st gets you back out. And of course, there's another little 1 over 2 pi j here. I'm putting that up, and I don't expect you to know it at all. Just be aware of it. This is, in fact, how mathematically there are certain transforms that are done. Right? If you look up if you have a textbook or you look up a set of transform tables, you would see hundreds and hundreds of Laplace transforms existing in table form. Those, many of them can be calculated from first principles, so you know certain functions and you could break it down in terms of other functions and then apply the transform. But others you have to work from principles back. And that would have been the case with this. So there were people who had to take that and actually do this is something called a complex contour integral. And there are special ways of evaluating these. It's not the scope here. I think if you do any of the advanced math courses, you may run across this. But it's not in our interest at this point in time. I needed to be aware of it, though, because there are certain things that you can't just simply look at table up. It may or may not exist. And the only way to find out, as I mentioned yesterday, is to kind of go through the mathematics of it. Right? Our method is to use data sheets like we do for design in electronics and elsewhere. So our data sheet for this is lookup tables. So you have to get it in our form, of course, before you can go and look it up in the lookup table. And that's where your the other technique that you should be familiar with, which is partial fractions. So the first thing you do, so a typical example, so here you have ys equal to something, and you want to apply the partial fraction technique to find yt. Well, the first thing you notice from this is that the coefficients n and m for the numerator and the denominator are not equal, right? Are equal. A proper transfer function, m is supposed to be greater than n. So if you ever encounter something like this, if you're working on a problem, first off, if you get a transfer function looking like this, and you'll see what happens when we find the answer. Something is wrong with the model, something is wrong with the system, or something is wrong with the mathematics, the calculation that was done, the algebra to get here, all right? But this is just for demonstration purposes. It's not supposed to be real. So if you're applying the partial fraction techniques to this, the first thing you have to do is to get it into proper form. So you need to divide the numerator by the denominator at least to reduce the s squared here. We need to get that down to at least s to the power 1. So if you do that, right, and you hopefully my algebra is correct, and you have to remember how to do your long division algebra as well, and it will come up later on towards the end of the term when we're talking about the Z transform too. You have to do some long division with that, and that one is a little bit trickier because the index powers are negative. So anyway, you divide until the condition where m less than n is achieved. Okay, and you do that. Once you do that, you will get this 7 minus, and we now have what we want here, which is what we call a rational polynomial. All right, you do that, and you proceed to factorize both the numerator and the denominator. Sometimes it could be done by inspection. So like in this case, you have the factors are s plus 2 and s plus 3 right here. And if you split it up into partial fractions, it's 29 over s plus 3 minus 12 over s plus 2. So that split up into partial fractions, the transfer function is now in this form. And our next step is to go and do what we said we would do. So you get it into our form, and then we go to our lookup table. So you go into the lookup table, you find a set of values. This 7 is a number. So the only thing, impulses transform into a single number. So a 7 is 7 by 1. So that means that the inverse transform of that is going to be some 7 delta t. 1 over s plus 3 is 1 over s plus a. So anything over an s plus a simple pole, s plus 3 and s plus 2 or s plus 15, s plus 0.5 will always give you an e to the minus at in the answer. So you look at the table, you zero into the things that match it the closest, and then you pull out the answer. So the answer to this thing is that yt is 7 delta t minus 29 e to the minus 3t plus 12 e to the minus 2t. Now that's the point I was telling you. When from the time you have a transfer function that gives you anything looking like that in it, in other words, the transfer function was not rational, m was equal to n. Because it was rational and m was equal to n, then the time domain response has an impulse in it. You don't want that. It means if I was to plot this, e to the minus 3t, that's a nice decaying exponent, right? So e to the minus 3t, right, would be something looking like that. E to the minus 2t would be something decaying a little gentler. But 7 delta t is an impulse at t equal to 0. Right? So it's an impulse weighted 7. Right? An impulse at t equal to 0 weighted 7. So you wouldn't want that. If you have a system like that and you put the thing and you turn it on, you're going to get an impulse response. That's going to blow your fuse or burn out something. Have a second. Yes, I had to take a call, sorry. So yes, so if you were to turn on a system like this, remember, we're back in the time domain. So this is what the system, this is the actual behavior. So at time equal to naught, certain things happen. At t equal to 0, when I turn it on, right? This is going to pop the fuse. 7 delta t means an impulse at t equal to 0. If I have an amplifier, it's going to blow the loudspeakers, all right, or burn a fuse, that kind of thing, or trip the circuit breaker in the house. So you never want that to happen, all right? Fair enough? Make sense? And again, the caution that I said before, if you're ever doing that and you get a problem that gives you that kind of transfer function, unless it's an what do you call it, an illustrative example to make you do partial fractions like this. If you're dealing with a real world problem later on when you're with Mr. Ramlal and you're doing controls and the like, if you ever get a transfer function that has a constant in it, before you convert it back to time, something went wrong. Go back into the problem and check how the problem is formulated and so on. Yeah. So homework will be this one, which is to try and find the inverse Laplace of this. So the same sort of thing, you figure it out, trial and error, do your divisions, do your fractions and the like, and see what you come up with. And of course, if you have MATLAB, it's a good way to check your answers as well. MATLAB has a function. I believe the command is root. I think it's root or roots, and you give it the coefficients. Right, so the coefficients of this would be 1, 9, 38, 66, and 36. You put that into some parentheses and tell it roots, and it's going to spit out the roots of that. Now it's going to spit it out. For instance, if the root with s equal to -1, it's going to tell you it. So the roots will be -1, -2j, whatever it is. If I were to ask you what the factor is, remember the factor is s plus 2j, s plus 1, etc. Okay? So always distinguish the sign between the factor and the roots. And coming back here a little bit before we go back here, right? If I were to plot this, let me go back here a little bit, right? We don't, at the point when we factor these, what do I call these? S plus 2 and s plus 3? What do I call that? These values? What do I call those? Poles. There you go. Right? So these things, s plus 2, s plus 3. So s plus 2, s plus 3. Those give me the roots of that, give me the poles of the denominator. Right? So this thing therefore has poles at s equal to -2 and s equal to -3. Okay? So where would those be located? If I were to draw it on the S-plane, s equal to -2 would be here, -2, and -3 would be something like this, right? Notice now, this is point 0. This is real, and this is imaginary. Imaginary, right? So the axis is going so. So these two values are on the left-hand side of the S-plane. You're going to meet this, but just as we have it here to point it out. They're on the left-hand side of the S-plane. This is the imaginary side here. So the real positive is this way. Real negative is on the left-hand side. And s plus 3 translates into, when I find the inverse transform, s plus 3, something over s plus 3, that's not getting this, something over s plus 3 gives me an e to the -3t when you find the inverse transform. And e to the -3t, as we saw here, e to the -3t is a nice decaying exponent. In other words, when I start this, whatever it is off, eventually it settles down or it goes to 0. So these sort of values, whenever you have poles that are on the left-hand side, right? When you translate that back into time, you always get a decaying sort of exponential behavior. And that means that the system will die out eventually. In other words, it is stable. As time goes to infinity, that particular thing will eventually die down to nothing. As opposed to another one, if it was 1 over s minus 3, when you translate that, you're going to get e to the 3t. E to the 3t does this. So a system with this and e to the 3t, that means the pole is at s equal to plus 3, which is on the right-hand side. That translates into a positive exponent, which means that this system, as time goes on, the system response gets bigger and bigger. You don't want that. All right, so this is just a preliminary thing. We'll talk more about it later on, but it's going to come up a lot in controls as well. Poles on the left-hand side, poles on the right-hand side, and poles right on the imaginary axis. Okay? And the last thing here is that you would have remembered this before. When the roots of the denominator are real, the solution will be in this form, a set of exponents. When the denominator roots are complex, that is when you have sinusoids coming in. So complex roots will give you a sine and a cosine somewhere inside of there. All right? So look at that. So if you have under the thing, you have a s, let's see what we had. S plus 1 minus 2j, for instance. This sort of thing, s plus 1 plus 2j, right? These sort of things would give you a sine or a cosine always in the answer, okay? You remember that from the examples that I did before, but it's a good general note to take. And we'll talk about that in the next follow-up part of this lecture. Another thing is that we usually, not always, but most times, complex roots occur in complex conjugates. Okay, so you know what complex conjugate numbers are. A good check for the mathematics of what you're doing is that if you get some roots and they're complex, it's somewhere inside of there is supposed to be a complex conjugate. If you don't, then somewhere in the arithmetic at our level, somewhere in the mathematics, there's an error. Okay? Or the problem was kind of contrived just to make you do some calculation just to see if you were able to do it. So, questions? Poles and zeros? Yes, Jamar.
Sir, I just have one question, and it's on page 11. I'm not really sure what you use to get the 17s plus the 22. I think you said that you have to do division in terms of like remainder theorem or something like that.
You have to divide, you have to do some long division. So you have to take this, so 7s squared plus 18s plus 20, and you divide it by s squared plus 5s plus 6, right? So you do that. So 7, the first thing is going to be 7, so you're going to get 7s squared plus 7 5s 35s, right, plus 42. 7 6s 42, something like that. Okay, so this, take away this now, is going to give you a 17, 18 and 17 is 35, and I can't read my own handwriting, 6, what we have here, 20 and 42 is going to give me the 22, right? Fair enough?
Yes, sir. Thank you.
All right. Yeah, you're going back to doing some high school algebra and the like. So you know, you always wondered where you would use some of these things. Well, here it is. All right. So any more questions on this part? We are having some heavy rain, and you might hear the occasional lightning. I'm hoping that we don't have any thunder. And anybody had hailstones from yesterday? All right, okay, so if not, let me finish this one and let's continue. Yeah, well, I'm not too sure where you are. I'm up north here, and it's very, very dark and very, very noisy. Yesterday there was some hailstone somewhere up, I think north central somewhere. It came down, the same sort of thing, some very dark clouds, and it took the moisture up. There we go, Aruka. All right, so if anybody has some snow, let me know. Okay, all this thing, climate change and the like. Right. Yes, you have to get outside occasionally. Yep, there we go. All right, so let's well, if it yes, go outside. Right, just like you have to go your hands up, out, down. Yes, you have to go outside occasionally. Right. Sounds like a science fiction movie. All right, so yeah, it is scary. I hope you all have your vaccines and so on, whatever brand is available. Yeah, there's plenty COVID outside, but you could look outside anyway. All right, so in part two of this section, I agree, Stephen. So sometimes, yeah, um, there you go. So in this part now, something again that you would have encountered, which is something called the initial value and final value theorems. They, as we said first off, that the Laplace transforms allows us to examine certain behaviors of a system without having to find the inverse transform. So for instance, we already saw that even in the time in the S-plane, depending on where the poles and zeros are located, I just pointed out to you that there were certain things that you could observe if the poles are on the left-hand side, that it means that the output is a decaying exponent. And then we saw that you could see things like the steady state response and the transient response and doing all of that without necessarily going into the time domain. Some of the things that you might be interested in, of course, are what happens before you even build a system. Remember, the Laplace transform is shorthand for us, it's our model. So what you may want to find out is wait a minute, I have this system, I have this model of a process plant that is doing something. If I change one of the variables, what is the initial reaction of the system going to be? Is it going to generate an impulse? Is it going to go unstable? And you'll talk about what unstable means in a little while. Or is it going to shut down? So that's what we call the initial response. As you turn it on, what is the sort of initial value that the system assumes? Now, of course, if you have the model, you could go the Laplace transform way, and you could find the inverse transform and then put t equal to 0 and so on. That's fine, nothing wrong with that, it's just cumbersome. Or you may say, okay, I have something, and I mentioned something like an incubator. So you have an incubator, and you change the temperature input on the incubator by 1 degree. And you want to see what happens. Does it settle down to a 1 degree change eventually? Does it not settle down? How long does it take? What is the final value it's going to take? Right? In other words, what is the steady state value of it? Again, you can take the longhand approach and plot it out. You do the inverse transform, and then you set t equal to a very big number and see what the value looks like. But we want to make use of the fact that we are in a domain, which is the S domain, that allows some of these things to happen even easier. And this is where these two transforms come in. That you have the final value theorem and the initial value theorem that allows us to do the evaluation of the system performance without necessarily having to come back into time. And you met this before, I think, in 1016 anyway. But here are some things. If you have a system and the response in time is e to the plus 3t cosine 100t. It's going to look like that diagram on the right-hand side. It's a sinusoid or cosinusoid, and the amplitude of the cosinusoid is going to increase. It's increasing exponentially. So eventually it's going to reach whatever is the power supply limit of the particular system and either stay there or the system is going to shut itself down or blow the fuse. What you say in a situation like that is that yt, the limit of yt as t goes to infinity, does not converge. It does not come down to an answer, right? So if you evaluate the limit of yt as t goes to infinity, you're not going to get an answer. It's not going to come down to something tangible. If you flip the sign around, and you have an e to the minus 3t instead, then what you get is a decaying sinusoid. So it's oscillating, but eventually it dies down and will come to 0. So the limit of yt as t goes to infinity, or as t gets very large, is 0. In other words, the answer converges. And that one is in fact a practical sort of signal. It could be intentional. For instance, an electronic doorbell, right, will give you that kind of performance. It rings and it dies off, right? A chime, a bell, a musical note, for instance, will give you that sort of behavior. You pluck a guitar string. It will oscillate, but the oscillations will die down as you go forward in time. And then you have these sort of things where you have an e to the 0t. In other words, it's just cosine 100t. That is a cosine is oscillating, in this case, between an amplitude of plus or minus 1. And it does not converge. It keeps the same amplitude forever. Again, you may or may not want this. That is the output from a signal generator, for argument's sake, right? It goes on and on and on and on, and it may be intentional. That's the output from your wall socket, except the amplitude, instead of being plus or minus 1, will go plus or minus whatever is the peak value of the wall socket voltage, right? So an AC power source will give you a voltage like that. So in some cases you want it. In other cases, if this is your audio amplifier at home, so you hook up your sound system at home and you have some big expensive speakers, and you turn it on and this is happening, you're going to get a high frequency whistle coming on the speaker, and it's going to burn up the thing if you don't do anything about it, right? Or your car, right? This is your audio deck in your car, for instance, and it's doing this kind of behavior. So sometimes you want the behavior, sometimes you don't. The usual one that you don't want is this one, right? That is does not converge, but it keeps getting bigger with time. So if you have a transfer function, yeah, there you go. Procrastinate. Yeah, we're putting off things, so don't do that. We only have a few weeks left, so if you keep going out, you're going to have an exponential load coming up on you. Good example, actually. So here's this. A system has a transfer function, and there you have it there. So what is the steady state value of gt? In other words, as t gets very large, what sort of response does this system give? Of course, it's fairly simple, so I could take the Laplace transform approach, put this into partial fractions, find the inverse transform, and then set theta a large number and see what happens. Or I could use something called the final value theorem. And the final value theorem simply states that if I want to find out what is the final value of some function in time, meaning what is the limit of the function in time as t gets very large, then in the Laplace domain, if I have the transform of gt, then I look at s times the transfer function of gt and see what happens as s goes to 0. So t going to infinity in time, the equivalent behavior is s going to 0 in the s-plane. So you take the transfer function. In our case, it's 1 over s into s plus 1. We multiply it by s, and then we set s to 0, and we see that the system eventually As time goes to 0, the limit of SGS is going to adopt a value of 1. The limit of G at T as T goes to infinity, according to what we say here, is going to be 1. And if you worked it out, you would have seen that the inverse transform of that was 1 over, would have been 1 over S plus minus 1 over e to the S plus 1, which was a step. So if you were to actually have done the inverse transform, you would have had a step response. So part 1 would have been a step response. Part 2 would have been a decaying exponent. So when you add the two of them together, right, the exponent eventually it starts, so the net output of that, if you add the two of them together, would be something looking like that. So as time gets very big, this assumes the value 1. It confirms. I mean, this is a straightforward example here. But the final value theorem basically says that if you want to find the final, what a system does in the long term, as t goes to infinity, if you can find the Laplace transform of it, or if you are already in the S domain, because this is where you're working, you can find out the initial value by setting S equal to 0, multiply S by GS, set S equal to 0, and you have the answer there. Again, this should be revision. I believe you would have met this already. Right? And then the other one, the other example now is, what is the sort of transient value of GT? In other words, when the system is immediately switched on, what is going to happen? The transient response we saw is what happens immediately after you switch on. But right immediately, as I switch on, all I'm interested in most systems is, does it ramp up to the voltage supply level immediately? Does it stay at 0 until I do something? Or does it have some other arbitrary behavior? That's all I really need to know. The most important one, of course, is, does it go up to its maximum as I turn it on? Because that's not what I would want. So same thing, you could do the Laplace transform, or you can do something called the initial value theorem. And the initial value theorem, again, is a sort of dual of what we had before. In this case, initial value is t going to 0. What happens in the S domain? S goes to infinity. Right? So to find the initial value in time, you look at what happens as S gets very large in the S domain. So you go back here again, we apply to the example that we have, and as S gets very large, S plus 1 becomes a very large number. So 1 over infinity goes to 0. And again, we could double check this one, luckily, because it's a fairly simple example. As t gets, when you now start it off, t is 0, so e to the t is 1, e to the minus t is 1. So the system starts at 0. And we saw that from the little plot. Right? Part 1 of the system looks like that. The step response and a decaying impulse. So at this point in time, when t is equal to 0, right, 1 minus 1 is going to be here. The net result, remember, the net result looks something like that. Yeah? So two important extra properties, extra values of the Laplace transform that we can make use of. The initial value theorem to find out what happens when you now start the thing. Once in the S plane, the limit of S, you take SGS and you send S to infinity. If you want to find out what value it is going to settle down to, you take SGS and you multiply and you set S to 0. Both of them will tell you how the system behaves. It doesn't tell you anything about what's happening in between. You can confirm to yourself that 1, the system starts either at 0 or at a very low level, and 2, as it goes on for a while, it at least settles down to some constant value. It doesn't keep increasing and getting bigger and bigger and bigger. Yeah. And here's just some values. Sorry, a little example just to revise on your own. What is so ys is gsxs, right? what is yt? Okay, so the transfer function of a system is gs, the input is that, the output is that. So what is yt? Well, if it's a transfer function, it means xs is 1. So you could try and figure out what yt is at that point in time. What will be the steady state value? Well, you could go from there. And then what will be the steady state value in response to a step change? So a step change means xs is a unit step that is 5 units strong. So you'll put that in and fiddle along with it and see what answer you come up with. Yeah, so any questions on that, which again should have been revision for you? Any questions or concerns? What to find yt again? Look it up. Why? So here's a system. The description here is a little convoluted, and perhaps the wording isn't the best, but it's to get you to think. The input to the system is x, and the output is ys. Right? So in other words, y is gs by xs. Gs is the transfer function of the system, which means that is the response when the system is, what do you call it? When the input is an impulse, 1. Right? So in this case, what we could assume, I think this was poorly written here. If the input here is 1, in other words, if x t is delta t, meaning that xs is 1, right, then ys is gs. So you could find the inverse transform here. Right? In exam, I would actually told you to maybe find ygp. Okay? It is a little contrived, but just to get you to think a little bit here. All right? Steady state value of the output of the system. So if the system is here, right? If at this point in time with an impulse, if you let xs equal to 1, right, you could get what the steady state value would be, and then if the input is a step change, then you could figure out what the output is going to be. All right. So 3 sort of things you're looking at. One, that the transfer function, the definition of a transfer function is the Laplace transform of the impulse response, which means that the input is an impulse. So if xs is an impulse, what is its value? Then what is the steady state value of that response? And then if xs is a step instead, what will be the steady state response of that system? Okay? Kind of 3 things in one. Right, so anything else? Any other questions? All right, so okay, so we take a short break again, a 5-minute break on that kind of thing. And then when you come back, strap yourselves in because we're going to start introducing something called convolution. All right, and we'll talk about it a little bit and get you thinking about what it means. All right, so go get some coffee, go stretch yourself, look outside if you can, walk outside if you can, and come back, and it's 1:51. So let's say about 5-6 minutes or so. So about 1:56, 1:57. So we will resume. Okay.